Hello, and welcome to our second video covering topics in section 1.2. In this video, we will start out with just some basic ways of talking about matrices. Then we will look at vectors from a linear algebra perspective. And finally, we will discuss the vector and parametric representations of solutions to systems of linear equations. All right, matrix basics. Suppose you encounter a matrix in the wild. Say something like this. What do you do with it? Well, the first thing you might do with it is you name it. And if you are going to name it, the tradition is to give a matrix the name, to name it with a capital letter. And usually you just start with A. So, all right, we'll name our matrix capital letter A. The next thing you might do if you find a matrix in the wild is classify it. And say this matrix that we found has 3 rows and 4 columns. And so it is classified as a 3 by 4 matrix. So rows come first and then columns when you're doing the something by something. For the record, I just could never remember this, and I think the problem was that because it's not alphabetical, like if it was, I could have gotten it straight, but for years I just had to look it up every time. And now the way I remember it is I say, "Oh, okay." My memory device is, well, if it was in alphabetical order, I wouldn't have had trouble remembering. So it can't be in alphabetical order. But all right, do whatever works for you. Or don't memorize it and just look it up like I did for a long time. I do appreciate a little bit of stubbornness. Okay, but you might be wondering, this matrix that you found in the wild, is it a coefficient matrix or an augmented matrix? Well, this may come as a surprise, but might not be either. And that's okay. We're soon going to see that matrices can be thought of as mathematical objects on their own. And in that case, we just might stop thinking about them as coefficient matrices or augmented matrices at all. And in fact, we'll see a little bit of that today. All right, some more basics. Suppose you had a general 3 by 4 matrix. How can we talk about a general 3 by 4 matrix, like behind its back? Well, all right, we give it some name, capital A, and then the entries we talk about, we give them usually whatever your capital letter is for your matrix. The entries in general are given the lowercase version and with these indexes. And the indexes are, so say you have entry little a sub ij. Well, that I corresponds to the row and the j corresponds to the column. So, for example, entry little a sub 2 4 says that this is the entry of matrix A that appears in row 2 and column 4. And indeed, it looks like I set this up right, and that is where it shows up. But what about a general n by m matrix? Well, okay. Similar principle, although usually you end up putting these little dots in there because, okay, you can't write down everything in general. But you would have your matrix A, the entries, little a's, and in, say, the first row, it goes from A11 all the way up to A1M. So there are M columns. So the last entry is the mth entry because that's the mth column. And then the rows, there are n rows. So you would index A11 all the way down to AN1. And then in the last row, you go from AN1, AN2, all the way up to A sub NM. Okay, just some real basic stuff about how to talk about matrices. All right, let's move on to terminology. An n by n matrix, so a matrix with the same number of rows and columns, is called square, mostly to be mean, but also because that is the shape that it makes. So, for example, here's a general n by n matrix. The entries A11, A22, all the way down to ANN, those entries are called the main diagonal, and that's just because they fall along the diagonal of the matrix. If you have a square matrix and it has zeros below the main diagonal, then that matrix is called upper triangular. That might be a little confusing to remember because the zeros are below. So why is it called upper triangular? Well, it's called upper triangular because the interesting entries all end up being in this upper triangular part of the matrix. So we think of the zeros as not being interesting. So if the zeros are below, then the interesting part is in the upper triangular part, and that is why it is so called. If zeros are above the main diagonal, then that matrix is called lower triangular because that's where all the interesting entries are. And finally, if you have zeros above and below the main diagonal, then such a matrix is called, wait for it, diagonal. All right, so got some terminology out of the way, which we actually won't encounter for like several sections. So, but all right, it's introduced in this section, so we talk about it here. But all right, the part I was looking forward to in this lecture, vectors from a linear algebra perspective. So let's actually first take a little trip down memory lane and remember back in Calc 3, in vector calc, how are vectors defined? Well, you go back to the Stewart book, which we use at our school. A vector is just a quantity with magnitude and direction. That is the definition. But usually we see them represented as a little arrow buddy, like so, where, all right, this is the direction and the length of the arrow is the magnitude. Or we see them represented as just a list of numbers, something like 5, 0 to -1 with these angle brackets. For the record, computers, they just think of vectors as these lists of numbers. That's all it is. That's all a vector is to a computer. You and I, we are smarter than computers. We have a richer understanding. We see them geometrically and as lists. So, okay, that's Calc 3. So what about in this class? Well, for now at least. A vector is a matrix with only one row or one column. So the row 1, 2, 3, or say this column 1, 2, 3. This is what a vector is in this class for the time being. You might notice this is very much in the spirit of the idea of a vector being just a list of numbers. Because mathematicians aren't always the most creative, we would call this first vector a row vector, and we would call this second one a column vector. And now, something that it shouldn't be obvious to you at all at this point, it turns out we will almost exclusively care about column vectors in this class. Again, nothing we've said so far should indicate why that is true. But as we'll see, column vectors are what we will end up using most. And these column vectors, okay, we still represent them as little arrow buddies. So the column matrix 1, 2, we could represent it in, all right, we've got 2 dimensions, and we think of these as being the coordinates of the tip of a vector, similar to how we did in vector calc. Okay. Now let's talk about how we would represent solutions to linear equations. So, okay, suppose we have this system here. We have 3 equations and 3 unknowns. Well, if we're going to solve this using the modern way, like let's first find the solution and then see how we can represent it. Solving this in the modern way, first we matricize the system. I know you thought I was done with that trademark gag, but I was not. Okay, so we matricize the system. We put all of our constant terms in the matrix. Then we refify the system. Again, no one will know what you're talking about if you say that outside of this class. But we put it in reduced row echelon form. We get something like that. And then we say, all right, let's translate back into a system of equations. So translating this reduced row echelon form back into a system, this first row would be x minus z equals 2, and the second row would be y plus 2z equals minus 1. And then this third row is just 0x, 0y, 0z equals 0. So we get these 3 equations. And now the strategy, if you want to, really understand what solutions are possible, the next strategy is you solve for the leading variable. And the leading variable is just the first variable in the equation. So we solve for the leading variable. And in the first equation we solve for it, we would get x equals z plus 2. And in the second equation, we get y equals minus 2z minus 1. And this third equation, 0 equals 0, all right, well, there are no variables there. 0 equals 0 is always true. That's not actually giving us any information for the system. So we're just going to stop worrying about that guy. So, okay, we've solved for a leading variable. And now, looking at the solution like this, we notice, okay, z can be whatever it wants, and any value we choose for z will generate a solution to the equation, or to the system. So for example, if we chose z equals 0, well, z equals 0 forces x to be 2 and y to be negative 1. And so then we would have the solution, x equals 2, y equals negative 1, z equals 0. If we let z be 1, then we would have, let's see, x equals 3 and y equals negative 3 and z equals 1. So there's our solution corresponding to z equals 1. And if we let z equal just some number t, then that would correspond to the solution x equals t plus 2, y equals minus 2t minus 1, and z equals t. And this right here is called the parametric equations for this solution. And parametric, referring to the fact that we're saying, all right, well, let z be any number t. This number t we call the parameter. It's the thing that we let change. And it's really to kind of distinguish from the fact that x, y, and z are the variables in our system, and t is like this parameter that changes, and as t changes, we get different solutions. So, okay, those are our parametric equations for a solution. And hopefully you, parametric equations in concept are familiar from vector calculus. Okay, we've got our parametric equations, and let's translate that into vector equation, the vector equation for our solution. So the vector equation for the solution, well, you start with the parametric equations, and you say, all right, let's take our variables and make a vector of the variables. So that's on our left-hand side. And then on the right-hand side, you make a vector just of the right-hand side of the equation. And then, okay, in one sense, whoop-de-doo, you haven't done much. You've just essentially put brackets over the information you already had. But now we do some manipulation. And the first thing we do is we separate the parameter from the constant terms. So we do this by saying, all right, let's make a vector with all of the t's. So we've got t minus 2t and t. So we'll make a vector of that. And then we'll have a vector of the constants. So 2, negative 1, and then there's a 0 here. And, you can just confirm, if you added these vectors together, yeah, you'd end up right back here. You'd get t plus 2, minus 2t minus 1, and t plus 0. Okay, so we've vectorized this, the variables on the right-hand side. Then we separated the parameter from the constant. And then our last step is to factor out this parameter. And this right here is where we wanted to end up. So the vector equation for the solution would look like this. You have your variables in a vector form, and then you have your parameter times a vector plus a constant vector. And the whole reason we would bother going through something like this, writing the vector equation like this, is because we have a rich geometric understanding of vectors. Let's use this to visualize what our solution would look like. How are we going to visualize this vector equation? Well, we have 3 variables here. So our solution is going to be something that lives in 3D space. And the way we do this, maybe this is familiar from vector calculus, but first I would take this constant vector and put that little arrow buddy on the graph. So this we go like 2, -1, 0, end up here. And then we're adding to that multiples of this vector 1, -2, and 1. So first we'll add 1, -2, and 1. Tip to tail addition says you add that vector, which, 1 -2, and then up 1. All right, maybe this isn't like the best drawing of that vector, but you get the idea. And then, yeah, we're not just adding this vector, but we're adding all multiples of this vector. And so this line right here represents all the solutions to this system. Any x, y, and z point on that line corresponds to a solution to our original system of equations. And as we can see, this corresponds to a system with an infinite number of solutions. Okay, let's do one more example. All right, let's have this system x1 minus x2 plus 4x5 equals 2, x3 minus x5 equals 2, and x4 minus x5 equals 3. So we have 3 equations and 5 unknowns. And all right, so let's matricize. And we get, all right, 1, -1, 0, 0, 4, 2, because 1, -1, no x3s, no x4s, but a 4 on x5, 2 here. Again, no x1s, no x2s, so we get 0, 0, 1 x3, no x4s, -1 times x5 equals 2, and then no x1s, x2s, or x3s, and then 1 x4 minus x5 equals 3. And then we want to rougify this. But hey, this is actually already in reduced row echelon form. Woohoo. Okay, we've got it in reduced row echelon form. Now our strategy is to go back to the system of equations, and translating back just actually gets us where we started because it was already in our REF. And then we solve for the leading variables. Now here, solving for leading variables gets us x1 equals x2 minus 4x5 plus 2. x3 gets us x5 plus 2, and x4 is equal to x5 plus 3. Okay, solving for these leading variables, we can see that, all right, well, we can let x2 and x5, they're free to be whatever they want to be. And any value we choose for x2 and any value we choose for x5, like totally independently of each other. We could choose something for x2, something for x5. And once we do that, we generate a solution. So any value of x2, any value of x5 chosen independently will generate a solution. And so what we do is we say, all right, well, let's let x2 equal some parameter s and let x5 equal some parameter t. And now our solution is where we would go through and say, all right, let's replace x1 or x2 with s, x5 with t here. So our solution looks like this. x1 equals s minus 4t plus 2. x2, well, that's just going to be our parameter s. x3, we've said is going to be t plus 2. x4 is going to be t plus 3. And then x5 is going to be t. And so here are our parametric equations for the solution. All right. We've got our parametric equations. Let's translate that into a vector equation. So we start just like we did before. We make a vector of our unknowns and then a vector of the right-hand side. Set them equal. And then we separate parameters from the constant, and we'll separate the parameters from each other. So we'll make a vector of the s, everything with s in it. So we've got SS0, 0, 0, because there's one s here, 0 s's in the last 3. Our t parameters, we've got minus 4 t's in the first one, 0 t's in the second, and then 1 t in the third. So that corresponds to that vector. And then our constants are 2, 0, 2, 3, and 0. And then as before, we will factor out the parameters from these parameter vectors. So we get s times 1, 1, 0, 0, 0 plus t times minus 4, 0, 1, 1, 1 plus this constant vector 2, 0, 2, 3, 0. And this right here, that is our vector equation for our solution. And again, the whole point of vectorizing solutions is so that we can have a concept of what the solution looks like. And here, okay, we have 5 unknowns. So we're in 5-dimensional space. And it turns out that this equation represents a 2-dimensional plane in 5D space. And you might think that this is not something that can be drawn in, just on a 2D like piece of paper or something, or on a slide. And you'd mostly be right, but I'm going to try anyway, because I want to like convince you that really this represents a 2D plane. And so let's start by just like take some point, call it our origin. Let's pretend we're in 5D space. And all right, let's put attach our constant vector to it. So we did. I've got this constant vector 2, 0, 2, 3, 0 attached to the origin. And now we're adding to that the vector 1, 1, 0, 0, 0. But we're also adding to it multiples of this vector -4, 0, 1, 1, 1. And we're not just doing it independently, but we're doing all multiples of this -4, 0, 1, 1, 1 vector and all multiples of this 1, 1, 0, 0, 0 vector. And so you make some choice for x, s, you make some choice for t, and then so you've got some multiple of s, some multiple of t, and you add them together, and using this like tip to tail addition, you get maybe some point up here, but it's really any multiple of s and any multiple of t. And it turns out that, okay, the solution is actually going to be this plane, the plane that is determined by these 2 vectors. And so the solution is you have these vectors, any multiple of these 2 vectors, that adding all of those up determines a plane, and then you just kind of shift that plane up by the constant vector 2, 0, 2, 3, 0. Okay, and I think that's all I wanted to cover in this video. So see you in the next one.